hard drives and SSDs. Together, they've been reading and writing our digital universe for decades. For someone running data centers that deal in exabytes, decisions about storage are big, and the consequences even bigger. I mean, it's not called hyperscale for nothing, so it's no surprise that here, hard drives and SSDs are used in combination. After all, they're fundamentally different technologies. Let's get into it. SSDs are built on NAND flash memory. This structure stores data in a silicon semiconductor cell in the form of electrical charges on a floating gate transistor. As silicon manufacturing techniques have evolved, shrinking the size of individual cells and adding more vertical layers of them has allowed for increasingly higher bit densities. Plus, without any moving parts, they're lightning fast, capable of processing data with sub-millisecond latency. But there's a trade-off. See, with NAND flash, data is written and rewritten using a program erase cycle. Problem is, if those cycles are run often enough, the cells begin to degrade and, unable to hold their electrical charge, eventually just stop functioning. And the higher we increase capacity per memory cell, the faster the cell's endurance diminishes. Now, techniques like wear leveling and over-provisioning that manage data placement within the device have been developed to address this gradual breakdown of write performance and memory cell endurance. But it all comes at the cost of efficiency. Truth is, this great technology is designed to be used specifically for read-intensive memory tasks. It always has been. Alright, so what about hard drives then? If SSDs are all about electrons and circuit board wizardry, hard drives are pure mechanical magic. Nanorobots that store and retrieve data using several rapidly rotating platters coated with magnetic material. The beauty of magnetic recording is that, powered on or off, this technology will read, write, and retain data without the concern of wear or electrons leaking. Its moving parts mean more physical points of failure and more latency in accessing data than an SSD, but with nanoscale precision design and rock-solid reliability, these things are built to last. And let's not forget, when data gets big, it gets expensive. Hard drives, simply put, are more economical than SSDs in dollars per terabyte, at least 6 times to be exact. And at this scale, the impact of those economics are magnified to the extreme. Now, our hyperscaler supports a wide range of workloads and services, and she knows that to get the best of hard drives and SSDs, a tiered architecture is where the smart money's at. Finely tuned file systems and software sit above the storage layer in her stack, automatically optimizing data placement. That sub-millisecond data access from SSDs make them perfect when random I/O and low latency is a must. But in reality, only a small portion of her data needs that kind of real-time processing. When it comes to big, unstructured data sets, like AI data retention, backups, and active archives, hard drives are her go-to, which is exactly why she stores 90% of her online data on disk. In the era of AI, storage choices matter more than ever. So bringing together the advantages of both these technologies just makes sense. Because it's one thing to get the job done, it's another to get it right.